Well, we are back again. Hello dear students. Before we start our work today, let us recap what we have learned till now from this lesson. First, we had proved a major point that the electric current produces a magnetic field. Second, electricity and magnetism are linked with each other. Third, we saw that Earth's magnetic field affects the magnetic compass. Fourth, when current flows from wire, a magnetic field generates by the flow of current through the wire. Fifth, we also learned how to chart out magnetic field lines. Earlier we saw in the first experiment that as the current passes through the circuit, the compass needle deflects, and when the direction of current was changed, the needle moved in the opposite direction. It was clear from the observations that the conductor was behaving like a magnet when the current was passed through it. It possessed the magnetic field under the effect of which the needle was getting deflected. Now I will show you how to measure and find out the magnetic field and its lines.
Take a piece of a cardboard. Insert a copper wire through it as shown here on the screen. Now sprinkle gently some iron fillings on the cardboard and pass the current through the wire, keeping the rheostat at a fixed position. Start gently tapping the cardboard for a few times. As you can see on your screen that the iron fillings have aligned themselves in a pattern of concentric circles around the wire. The pattern on the cardboard represents the magnetic field lines. Arrows shows the direction of the magnetic field produced due to the current passing through the wire. Now if we increase the current in the circuit, the deflection also increases. Take the compass further away from the conducting wire. The deflection in the needle decreases. So this shows that the magnetic field produced by a given current in the conductor decreases as the distance from it increases. To know the direction of the magnetic field associated with a current carrying conductor, the right hand thumb rule is used.
Imagine that you are holding a current carrying straight conductor in your right hand in such a way that the thumb of that hand points towards the direction of current. Your fingers will be wrapped around the conductor in the direction of the field lines of the magnetic field. This is called right hand thumb rule. You need not hold the wire really, just imagine it. Let us do one example. Consider the power is passing through a east to the west direction in the horizontal manner. So this is the east direction, it is the west, so it will be north and this will be south. Now see, what will be the direction of magnetic field above the conductor as well as below the conductor. As direction is from east to west, this is north, this is south. So above the conductor, direction will be from south to north, and below it from the north to south. In this manner, you can able to find out what will be the direction of the magnetic lines of forces if the current is flowing through a conductor.
Now let's see what happens when we bend the straight conducting wire in the form of a circular loop and pass the current through it. Just imagine the shape of magnetic field lines. How would they look? We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. Corresponding to each point on the loop, the magnetic field is represented by concentric circles. These circles would become larger and larger as we move away from the wire. As we reach the center of the loop, the arc of the large circles would appear as a straight lines. So the magnetic field produced at the center of the circular wire is proportional to the current passing through it and is inversely proportional to the radius of the loop. If there is a circular coil having an n turns, the field produced is n times larger than the field produced by a single turn. If the current flows in the clockwise direction, the magnetic field enters into the plane and the force behaves like a south pole. If the current flows in the anti-clockwise direction, the magnetic field comes out of the plane and force behaves like a north pole. Take a rectangular cardboard having two holes. Insert a circular coil having a large number of turns through them normal to the plane of the cardboard. Connect the ends of the coil in series with a battery, a key and a rheostat as shown here. Sprinkle iron fillings uniformly on the cardboard. Plug the key. Tap the cardboard gently a few times. Note the patterns of iron fillings that emerges on the cardboard.
If you want to understand the event of magnetic field when current passing through a solenoid, first of all we should know.
What is a solenoid? A coil of many turns of insulated conducting wire wrapped closely in the shape of a cylinder is called a solenoid. If a solenoid has n turns, then the magnetic field associated with it is n times stronger than that due to one turn. This is because in each turn the direction of the current is same and hence the magnetic field due to the current in each turn will be added. Because of this fact, a strong magnetic field is obtained using a solenoid as shown. Magnetic field of a solenoid is quite similar to that of a bar magnet. In this view, one end of a solenoid behaves as a north pole, the other as a south pole, and the magnetic field is the same at all points inside the solenoid. That is, the field is uniform inside the solenoid.
Choose the correct options. The magnetic field inside a long solenoid carrying current first is 0. Second, decreases as we move towards its ends. Third, increases as we move towards its ends. Fourth, is the same at all points. Fourth is the correct answer. The magnetic field will be same at all points inside a solenoid. Now we have seen when a magnetic needle is placed near a current carrying conductor, it experiences a force and deflects. We know nature prefers symmetry. So, when a current carrying conductor is placed near a magnetic field, it also experiences a force. Before I explain you this phenomena, let me explain some terms. First is the commutator, a device that reverses the direction of flow of current through a circuit is called a commutator. Second, armature, the loop wound on a axis along with the commutator is known as an armature. Now look at this phenomena through this experimentation.
Take a small aluminum rod, suspend it horizontally, place a horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field directed upwards. Connect the aluminum rod in series with a battery, a key and a rheostat. Now pass the current in the rod. The rod will be displaced. Now reverse the direction of current. This time, rod will be displaced in reverse direction.
What does this activity suggest? This activity suggests when a current carrying conductor is placed near a magnetic field, it is experienced by a force. And when the direction of the magnetic field is changed, the force direction is also changed. And when the direction of the current is changed, then again the direction of the force is changed. How the displacement of the rod will be affected if first, current in rod is increased. Second, a stronger horseshoe magnet is used. And third, length of the rod is increased. In all these three cases, the displacement of the rod will increase because force acting on the rod will increase in all the three cases. It shows that the direction of force on the conductor depends upon the direction of current and the direction of the magnetic field. Now the question may be arising in your mind. When does the conductor experience maximum force? The conductor will experience maximum force when the direction of the current is at right angles to the direction of the magnetic field. This is Fleming's left hand rule. Stretch your thumb, your forefinger and your middle finger such that all are mutually perpendicular to each other. If your forefinger indicates the direction of the magnetic field and the middle finger gives you the direction of current, then the force experienced by the conductor will be in this direction where this thumb is giving you the direction. In this manner, you can able to find out what is going to be the direction of the magnetic force experienced by the conductor. Let us do one example. An electron enters a magnetic field at right angles to it as shown in figure. Find the direction of force acting on the electron. We can able to find out the direction of force acting on the electron by Fleming's left hand rule. See, in the figure you can see it is like this. It is giving, the thumb is giving the magnetic direction. The electron's direction is showing by this. So where is the direction of force? You can see it. It is inward like this. Which of the following property of a proton can change while it moves freely in a magnetic field? First, mass. Second, speed. Third, velocity. Fourth, momentum. Velocity and momentum both can change. So I think now you have got enough idea about the relation between the electric current and magnetic field. In the next episode, we will see how this relation can be used for humankind advantage. Before we part, let us revisit our lesson today. In our lesson today, we have learned that flowing electric current creates a magnetic field. We have also learned to chart the direction of magnetic field and magnetic field lines by right hand thumb rule. What is a solenoid? The conductor will experience maximum force when the direction of the current is at right angles to the direction of the magnetic field. And last, Fleming's left hand rule. Hope you have understood today's lesson. Be ready with the revision for the next episode of the same lesson. Till then, goodbye.